Day 3, Unit 5, Ordinary Annuities is the topic. The lesson goal is I know what an ordinary annuity is, and I can represent it with a timeline. And I can use the ordinary annuity formula to determine the future value of an investment. So that's the value later. Also, I need to know that I am able to work with compounding periods. So I need to know how many compounding periods are in a year for semi-annual, monthly, quarterly, weekly, and daily compounding periods. I also need to have the skill that I can write the annual percent rate as a decimal. Independent practice for the day is textbook on page 498, questions 4 to 6, 10, and 11. Annuities then. Annuities, or an annuity, is a series of equal deposits or payments made at equal time intervals. So those could be weekly, they could be equally monthly, they could even just be equally annually. When deposits are made at the end of the time interval, so at the end of the week or the end of the month, then the annuity is named an ordinary annuity. If the payments were made at the beginning, then we would call it an annuity due. Also, you need to know that the total value of all the deposits at the end of the last time period is the amount of the annuity. So we're saying total value, that is all the previous deposits have been earning interest, and when you put in your last payment, the last right at the very end of the annuity, that's the amount of the annuity. And that's also sometimes known as the future value of the annuity. So example 1, we are going to use first principles, and that means that we are going to consider the timeline from each deposit, and we are going to move the timeline forward till the end of 3 years, considering each one as compound interest. Okay, so it says suppose you deposit $250 at the end of each year into an investment account that pays 4.5% compounded annually. So since it's compounded annually, then I'm only receiving interest once a year. The question is, what is the amount of the regular deposits after 3 years? So I've drawn a timeline, and I've only made ticks for each year because that's how often I am making deposits. So the deposit amount is $250, and that's at the end of each year. So at the end of year 0, we're basically at the beginning of year 1. Off by a day. So I'm going to write down 250 here, 250 at the end of year 1, and 250 at the end of year 2, which is the beginning of year 3. All right, so if I consider interest being earned, the amount of money, $250, paid at the end of year 2 doesn't have any time to interest, so it's just going to be $250. But the money that was put in at the end of year 1, so the beginning of year 2, has a full year to accrue interest. So this is 250, and we multiply this by 1 plus, I need 4.5% as a decimal, so 0.045, and that's to the power of 1. The money that was put in at the end of year 0, so very close to year 1, has year 1, 2, and 2 to 3 to accrue an interest. So I'm going to bring my timeline down, and the interest that is earned as well as the principal, so the future value of the payment at the end of the year 0 is 250, the principal, times 1.1 plus 0.45, which is my interest rate, and this is all to the power of 2 because it wound up having 2 full years to accrue interest. So altogether I have the $250 that I just made, the $250 with 1 year of interest and the $250 with 2 years of interest because of my regular deposits for 3 years. Summarizing here then, we did first principles, so we considered each payment as an original compound interest using I as 0.045 since it's annual compounded. And each payment or present value was $250 when you put the money in at each time. And this payment is accruing interest. So here I had no interest accrued because it was just deposited. Here I had 1 year of interest accrued because it was deposited 1 year ago on the timeline. And here I had 2 years of interest because this money was put in 2 years ago on the timeline. So the total value in the future, that is at the end of 3 years, altogether is these things added together. So calculating each of these interests then, I wind up with $250. $250 plus interest is $261.25, and $250 plus 2 years of interest is approximately $273.01. And I have the dot over the equal sign to say approximately. When I total this then, I get $784.26 was the value of my $250 regular deposits for 3 years, compounded and paid annually. As you can probably imagine, if we had a lot of payments that were made, say payments made weekly for 5 years, then you would have, 52 times 5 number of payments. So it would be very painful to have to draw the whole timeline and work each of these present values out, future values out for each payment. So we have a formula. So the formula is here, A, which is the amount of the annuity, so the future value of the annuity, has a worth of R, which was the regular payment, so we had just done that as $250. And we take that and we say the regular payment times, so this is all in brackets, and then a smaller bracket, 1 plus I being the interest rate per compounding period. So we had used 0.045 because the payment was a year, so we didn't have to divide 4.5% into any payments in a year. And that's all raised to the power of n, where n is the number of compounding periods in total. Okay, so in your full investment. And then you subtract 1, close your bracket, and divide all of this by the value of I again. So we're going to use the formula now using R as 250, N as 3 because it was 3 years of investment, and I as 0.45. Okay, so I'll write my formula. A equals R, which is 250, bracket, smaller bracket, 1 plus 0.045 to the power of 3. I'll subtract 1, close my brackets, and divide by 0.045. And this can be calculated on the calculator using the brackets as indicated. And when we use the calculator in this method, we get the answer $784.25625, which would round to approximately $784.26, which is the value we found previously. So this is a much more efficient method for calculating the future value of an annuity. So example 2 then, we're going to use the same formula because we're practicing it, but it says suppose you make regular deposits into an account. So I know I'm going to use this formula right now because I'm talking about the R, and it's the only one I have for regular deposits. You deposit $1,000 every 6 months into an account that pays 6% compounded semi-annually. What will the amount be after 10 years? So since it's an amount afterwards, I know that I'm talking about the future value again. And that's what A calculates, is the future value. So we do have the correct formula. So I'm going to decide what R is, and here it says I'm making regular deposits of $1,000, so R will have a value of 1,000. It says that I am paying interest of 6%, semi-annually. So I'm going to need to convert 6% to a decimal and divide by 2. So that calculation isn't rounded, so I can just use 0.03. And n is, let's see, I'm making it for 10 years, but I'm paying twice per year, so I'm actually going to be making 20 payments. So altogether then I am paying $1,000 20 times, that is every 6 months for 10 years. And the rate that I'm earning each period is 3%. So filling in the values for R, N, and I into this formula, I have A equals 1,000 times double bracket 1 plus 0.03, because that's the interest rate per compounding period, to the power of 20, and 20 is the total number of compounding periods. I subtract the 1 as in here, and then close that bracket, so this total value will be divided by 0.03. Typing that into the calculator, I get $26,870.37 approximately, and so I have rounded. What would the value have been of the amount of money that I actually paid? Well, if I made 1,000 payments, or $1,000 payments, and I made apparently n payments of $2,000, I could calculate the payment total, which is really the amount invested. So that's going to be 20 times 1,000, or in other words, I invested $20,000, but in the end I wound up with $26,870. So the interest earned over those 10 years is the difference. So $26,870.37, subtract $20,000, so I have $6,870.37 in interest. So we have seen two examples of using the new formula where we have payments made at the end of each period for an annuity. I recommend you try these questions now, because the third example we're going to be using the formula, but we're going to be rearranging the formula to find R. So if you're not familiar with the new formula, there will be difficulty understanding the next example. Okay, so now we're going to be using the future value of an annuity formula, the A equals R to the blah 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 divided by I, to calculate the regular payment value. So I need to find the R this time, which means I need to know what I is, I need to know what N is, and I need to know what A is. Again, remember A is referring to the future value. So I'll read my example. Suppose you begin a savings program to have $2,500 after 5 years. So that's a future value. So that's going to be my A of $2,500. This is supposed to be for after 5 years. It says I'm making regular deposits, so that's going to be the R value that I'm not sure of, and it's every 6 months. Notice this compounded semi-annually. Those two values match. Every 6 months means semi-annually. So you make regular deposits every 6 months into an investment account that's paying 6.5% interest compounded semi-annually. We need to calculate the regular deposit. Okay, so what do we know? So we know that the A value, the future value, is 2,500. We know the I value is 5.5% annually. So semi-annual compounding, I have to divide by 2. So I'll calculate that out. And that's 0.0275. And I also know that the number of compounding periods in the investment is 5 years times twice a year, so that's 10 altogether. So if I substitute this into the formula, then I get $2,500 is equal to a payment that I'm not sure of times 1 plus 0.0275, all to the power of 10, subtract 1, and I'm supposed to divide all this by 0.0275. Well, there's only one unknown here, the R value, so I can rearrange in order to solve R. So the first thing, since this is all divided by, I need to know all this whole value to get the answer for A usually before I divide. So I'm going to undo that by multiplying by the I value, the divisor. Okay, so multiplying by 0.025 on one side will cancel the divisor, and multiplying by 0.0275 on the other side. So what is the result when I multiply 2,500 by 0.0275? So I get a value of 6875, and I don't want to round here. And that's equal to R times everything in that bracket. So if I could actually simplify or calculate everything in that bracket, then that'll be easy to isolate R. So I get a value of 0.3116510325 approximately. And I'm going to need to isolate R, so I'll do that by dividing by this decimal 0.31165100325 on both sides. So when I multiply through, these values will cancel. This leaves me R on the right hand side, and the calculation I came up with was 220 point, and this is a money value, so I will just use 2 decimal places, so I'm going to round it to 60 cents. So we have now answered the question. The regular deposit that has to be invested every 6 months to have a final future value of $2,500 is a payment of $220.60 if I'm earning 5.5% interest rate compounded semi-annually.